Picture a vector B in three-dimensional space projected onto a plane, the column space of a matrix A. The projection, P times B, lands right on the plane. The arrow vector E floats perpendicular above it, reaching from the tip of the projection up to the tip of B. Now, two extreme cases matter. First, if B already lies on the plane, then its shadow matches it perfectly. The projection equals B itself. Second, if B points perpendicular to the plane, then its shadow collapses to zero. The projection is the zero vector. These two extremes reveal everything about how projection works, and they expose a second projection matrix that you get for free. The projection matrix P equals A times the quantity A transpose A inverse times A transpose. For any vector B, the product PB gives the closest point in the column space of A to B. The column space, written C of A, is the set of all vectors expressible as AX for some vector X. In other words, P takes any vector and drops it onto this subspace. Let's now make the two extreme cases precise. First extreme case, B already lives in the column space. That means B equals AX for some vector X. Now let's substitute this into the projection formula. PB equals A times the quantity A transpose A inverse times A transpose times AX. We can regroup the inner terms. A transpose A inverse multiplied by A transpose A. That's a matrix times its own inverse, and that equals the identity matrix I. So we get A times I times X. That simplifies to AX, which is just B. The projection of B equals B. Projecting a vector that already lies in the column space changes nothing. The shadow coincides with the vector itself. One important note, this means P acts as the identity on its own column space, but P is not the identity matrix on all of Rn. Vectors outside the column space do get changed. P only preserves what's already in C of A. Now the opposite extreme, B is perpendicular to every vector in the column space. Perpendicular to the column space means B lies in the null space of A transpose, written N of A transpose, the set of all vectors where A transpose times B equals the zero vector. Let's substitute this into the projection formula. P times B equals A times the inverse of A transpose A times A transpose B. Focus on the rightmost piece, A transpose B. By our assumption that B is in the null space of A transpose, that product equals the zero vector, so the entire expression becomes A times the inverse of A transpose A times 0. Any matrix times the zero vector gives 0, therefore PB equals 0. The projection annihilates B completely. A vector perpendicular to the plane casts no shadow. There is no column space component to capture. Every vector B combines these two extremes. We can write B equals PB plus B minus PB. This is just adding and subtracting the same thing, so it's automatically true. Now factor B out of the second term. B equals PB plus the quantity I minus P times B. Let's label these pieces. PB is the column space component. That's the part of B that lives in the column space of A. And I minus P times B is the perpendicular component. This is the error, the part of B that's orthogonal to the column space. These two pieces are orthogonal to each other, and together they reconstruct B completely. So what does P do? P keeps one piece and kills the other. It preserves the column space component and eliminates the perpendicular part. Now here's an interesting observation. I minus P turns out to be a projection matrix in its own right. Let's verify that claim. A matrix qualifies as an orthogonal projection when it satisfies two properties. It must be idempotent, meaning it equals its own square, and it must be symmetric, meaning it equals its own transpose. Let's check idempotency first. We need to expand I minus P quantity squared. Write it as I minus P times I minus P. Now distribute I times I minus I times P minus P times I plus P times P. That simplifies to I minus P plus P squared. Now here is the key fact. P is idempotent, so P squared equals P. Substitute p in place of p squared. We get I minus p plus p. Combine the terms involving p. Negative p minus p plus p gives negative 2p plus p, which equals negative p. So our final result is I minus p. We have shown that I minus p, quantity squared, equals I minus p. Idempotency is confirmed. Now let's check symmetry. Take the transpose of I minus p. The transpose distributes across the subtraction, giving us I transpose minus P transpose. The identity matrix is symmetric, so I transpose equals I, and P is symmetric by assumption, so P transpose equals P. Substituting these in, we get that the transpose of I minus P equals I minus P. Symmetry confirmed. Now let's summarize what we've established with a comparison. Both P and I minus P satisfy the two conditions for an orthogonal projection matrix. First, both are idempotent. M squared equals M. Check for P and check for I minus P. Second, both are symmetric. M transpose equals M. Check for P and check for I minus P. As for what they project onto, P projects onto the column space of A, while I minus P projects onto the null space of A transpose, which is the orthogonal complement of the column space. One important warning: idempotency alone does not guarantee an orthogonal projection. A non-symmetric idempotent matrix produces what's called an oblique projection. The decomposition is not into perpendicular pieces. You need both conditions: P squared equals P, and P transpose equals P. Here's the complete picture. P and I minus P decompose all of Rn into two orthogonal subspaces. P projects onto the column space C of A. I minus P projects onto the left null space N of A transpose. Every vector B splits cleanly. B equals PB plus I minus P times B. This is just the column space component plus the perpendicular component. We can verify this is trivially true. PB plus B minus PB simply gives B, and the two components are orthogonal because PB transpose times I minus P times B equals B transpose P times I minus P times B, which equals B transpose times P minus P squared times B. And since P squared equals P, this is B transpose times 0, which is 0. No overlap, no gaps, a complete orthogonal decomposition. This decomposition drives least squares regression, where PB is the best fit, and I minus P times B is the residual. It also powers signal processing, separating signal from noise. One matrix P and its complement I minus P, two projections that together account for every vector in the space.